Hello there. Einstein used to say that if you really understood general relativity, you could explain it to a very young person. So let's do that. So first we're gonna by just I'm trying to get my red arrow here. There we got it. We're going to show the relationship between mass and energy, the famous E equals mc squared, but we're going to drive it by inspection. So that we understand it, where it comes from. Then we're going to show not only that mass curves space-time, but we're going to show why it and how it curves space-time. And then we're going to use that understanding to create the beginning of a formulation of a model of general relativity. Then we're going to review special relativity. Now, I did in my GR 1 and 2, I went through and derived in great detail special relativity and also derived the Lorentz transformations from geometrical ideas, just to prove that, well, more than that, but to prove that the theory was correct, and which it was and is. So we're going to review enough of special relativity to derive the invariant for special relativity, and specifically the one proposed by Minkowski, which is the same invariant used by Albert Einstein. So we're going to keep that for consistency, and also it's mathematically works out to be a clean way of doing it. Then we're going to construct a procedure. Like I'm a design engineer, so I like to have this product specification and I design accordingly. And when I actually came up with this myself, I like to do things, let's just say, I don't mind doing things in parallel and doing it again, even though other people have developed it. I want to have the feeling of having developed myself. So in this case, I had designed this procedure and it actually came up with the same one, but it's kind of a funny thing because you'll see that I'm not going to give it away. Construct a procedure designed specifically to extract the invariant from special relativity, which I've concatenated as SR, starting out with measurements from curved spacetime. So it's almost like you force fit the model to produce the result you want. And I thought, anyway, it makes me laugh because it's kind of like a crude procedure. It's like using a sledgehammer to get what you want. But it works, and that's the funny part. Right, and part of my irreverence, even though Einstein was brilliant, and the people who did the solutions to the gravitational field expressions after were also very brilliant scientists and all that, but I still like to joke and make fun of things, partly to keep awake, and hopefully it'll help you keep awake. They make the procedure sound respectable by calling it the metric tensor. Now, when you design the procedure to do what you need to do to extract the same metric as special relativity out of the situation, the measurements of pertaining to highly curved spaces, when you do that, it's very clear what you've done, and it's easy to understand. But it's almost like a lot of physicists, and here I'm kind of joking a bit, but it's almost like they hide their tracks. It's like sweeping the earth with a branch with leaves on it, you know. And they come up with this thing. It's actually two parts, and you'll see that later. And that part all makes beautiful sense, but they change it and they call it just G, a little small G, and then they call it the metric tensor, which is kind of scary, and it sounds kind of respectable, But it doesn't help you to comprehend that. So we're going to get around all that. And I hope you find it as funny as I do. And then we determined, again by inspection, that the metric tensor multiplied by its inverse is equal to 4. And that turns out to be key, the number 4. Like I'm talking, that's why you can explain it to young people, because the number 4 plays a big role in this explanation, as it turns out. So then we use the parts that we've dug up so far to derive Einstein's gravitational field expression in full. Well, in full the way that Einstein did it, from the initial model that we started with. That's the first step, plus using just the ideas of the metric tensor and its inverse, which we'll discover. So all of this has to be very simple, and it is. And I'm going to try to get through it quickly. Keep it lively here. Okay, so by inspection, energy and what is energy? So we all know that energy is equal to force times distance. And if you ever pushed a car, you can feel that it becomes very evident very quickly. That as you increase the distance that you're pushing, you feel that you're more and more drained of energy. And force is equal to mass times acceleration, and then so you multiply that by distance, and acceleration is meters per second squared, metric units, mass is kilograms, and distance is meters. So you multiply those units together, and you get kilograms meters per second, which is velocity or speed squared. It's actually speed, it's not a vector, there's no direction in the way we're talking about it at the moment. So energy is equal to kilograms times the speed squared. Now in General Relativity number 1 and 2, we measured the inductance. I first of all designed an apparatus to measure the inductance, and the capacitance of the vacuum. And using that, it becomes evident, again by inspection and by other methods, if you need to use other methods, it becomes evident that everything in the universe travels at one speed, and through the vacuum, and that speed is equal to c, and in astronomical units you say the speed of the c is equal to 1. So all undulations in the vacuum travel at the speed c equals 1. And mass, is an undulation traveling through the vacuum at the speed of light. So when you say energy is equal to kilogram times speed squared, there's really only one speed that applies, and that's the speed of light. So energy is equal to speed squared is equal to mass times c squared. That's the only sensible result. So by inspection, we just derived that energy equals mc squared. Now a lot of people might not like being able to go in there and look and just see what's going on by inspection, but I don't really care. I've never really worried too much about what other people think. I care in some sense, but not very much at all. I'm happy to have different people have different views on things. So I want to talk now about why mass would, or even energy, the same, equals mc squared. So the two are convertible. Why mass curves space-time? So I want to show you actual photographs here of the nuclear bomb at Hiroshima, which a very horrible thing. It converted 0.7 grams into energy. Now, 0.7 grams is that's about 30% the mass of an American dime. And such a small mass, when converted to energy, released the equivalent of 15,000 tons of TNT. 15, you know what a ton is? It's what, 2,000 pounds? 15,000 of those blowing up all at once. Horrific explosion. And it's only 0.7 grams. So I want to show, and so here we have the, down on the lower right-hand side, we have a picture of the bomb used in Hiroshima. And then we have a little bit moving towards the left, picture of when the bomb first went off. And then we have it a little bit later, it's expanding, and you see the hot gases coming out the top there, and radiation. That small amount of mass is converted into an enormous amount of radiation and particles and all sorts of things coming out of there. And then I show another picture of a giant head still expanding. And we have all the shark, and the previous one, you can see the shock waves, those rings moving out, knocking buildings down, trees down. Now, what I want, and the green lines, green arrows, I want to think about compressing that free momentum of that 0.7 grams of energy back into the small space of the mass, the initial mass. And what you need to do to convert that outgoing momentum into inward flowing momentum is you need to interact with a lot of changes of momentum. And change of momentum is equal to force. Force is equal rate of change of momentum. So you need a lot of force to push all of that radiation back into the material, the small portion of the material in that bomb, the part that was uranium. So this force results in extremely high pressures. And as in any structure, the loads eventually work their way down to the substrate underneath. And for matter, for mass, the substrate is space-time itself. And so these pressure forces push out on space-time itself, because that's the only thing holding it in there, because it wants to expand. And so that the high pressures push on space-time, push outward against space-time, and curve it. So let's talk about the curvature of that the Earth imposes on the space-time near it. And I want to say, when I talk about the curvature of the Earth, I'm not talking about the curvature of the globe of the Earth, you know, the planet Earth. I'm talking about the curvature that the Earth imposes on the space-time very close to it. And I worked it out. It's a simple calculation, but we don't need to do that here. And it works out to be 9.92 times 10 to the 10th meters. That's the radius of curvature. So you imagine you have a string, and you know, if you have a short string, it curves around, 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 around. But if you have a string, let's say 100 miles long, and you move it, it seems to be going straight. Well, imagine if you have a string, what it works out to be basically 100 billion meters long, which is 100 million kilometers. So 100 million kilometers long string. When you walk with it, it's going to be an almost perfectly straight line. So that's in other words, the curvature imposed by the planet Earth on the space near the Earth is actually almost flat, but it's enough to cause gravity as things move through time. They go through the curvature of time, like space-time, right? So time is curved and space is curved, and mass goes straight up through time, and it gets bent by the curvature of the curved space and moves in on the Earth. So I don't want to go into that in super details, but I did want to explain curvature and energy, and we just did that. Remember, I'm explaining it to what would also be understandable by a very intelligent young person. So when we do physics, we want to keep it tidy. People like to put things in tables, and it took me a while to get used to that because it's hard to keep, you know, rows and columns steady. I'm separated. And anyway, so as part of the organization principle, let's look again at mass. So energy equals mass times c squared, which is, let's go up here, I'll use my handy dandy arrow again. Energy is equal to mass times c squared, which is c times c. Now, we live in four-dimensional space-time, you know, 3 dimensions of distance and 1 dimension of time, which is the direction actually that the mass is traveling we call that time. So C has 4 directions that it can point. So there's 4 degrees of freedom. And so mc times c, which is mc squared, then has 4 times 4, and 16 possible directions. So in order to cover all the possibilities, and one thing about nature, and maybe people don't talk about this very much, but it's kind of like a school kid going out and playing in the field at recess. You know, they climb up every tree and turn over every rock. I mean, they're exploring all their degrees of freedom, so to speak. And nature does that same thing. So if there are 4 times 4 possible directions, and you put that in a 4x4 table, nature's going to, under different circumstances, explore all of those. So you need to have them. So what they do is they put it into a 4x4 table, which is 16 terms, and they call them the energy densities which are energy is equal to mass times c times c. And to get the density, you just divide by the volume. So they call that table UV, and UV is because you have 4x4. It's the indices for those 16 terms. So they put it in a 4x4 table, and they call it the stress energy tensor. Stress because, you know, the energy is pushing on the mass, and energy and mass are exchangeable. So they do the same thing. They push outward on if they're contained within a volume, they have to push outward on space-time and curve it. Okay. So we have we put the stress energy components, the mass density or the energy density, it doesn't matter, you just tweak the units a little bit, into TUV, and then you got on the other side, because the curvature depends on the mass density, right? So, and the curvature is also in a 4x4 table for very similar reasons, and they call that the curvature tensor. So it's R subscript UV. Now, we can at this point, because we have the intuitive understanding, like Einstein did, that there's a direct relationship between the mass density in a particular volume, the mass density in that volume, a constant volume, is related to the curvature by some, and what would you think? A constant of proportionality? That would be the first thing to do. So let's write that down. So here we just write it down. And it's wrong. But it's the first step, and it's the same step that Einstein took. So let's take that step, and we'll see where it leads us. So R subscript UV is equal to the constant of proportionality times T subscript UV. And let's use that as the initial thrust into a model of gravitation and mass and curvature. And so let's move on. Now, I'm interfering with my charts. I'm moving myself down. That's good. At least I'm floating. I like floating. So this diagram looks so scary, but it's not. I'm going to show you. See the triangle there? You see the yellow triangle? Here, I'll use my handy dandy again. See, A, G, H. So there's a triangle. I don't know how I came up with these letters, but anyway. AGH is a triangle. Now, do you see a right-angled triangle in there? Now, right-angled triangles are great because you can use Pythagoras, the Pythagorean theorem. Now, every carpenter has to know the Pythagorean theorem, otherwise when they design a window, it would not work. The glass wouldn't fit. Doors would not fit in there, You need that's a basic principle of Euclidean geometry. Well, it turns out it's a basic principle also in special relativity, and again, it has applications even in general relativity. So, but with an extended scope of application. So let's, and so let me say that again, AGH. Now do you see another right-angled triangle in there? And I bet you do. And there it is, in red. Okay, so we got, and then the other triangle is BGH. So what the heck is this? What I've shown is actually, it's a momentum diagram. Or it could be mass traveling. And mass always travels at the speed c. So we have through the vacuum, and mass, but they don't always go in the same direction. So you can have masses, both of which are moving the speed c, moving at pointed in slightly different directions. So the direction that any mass is going is the direction that we call time, and Einstein called it their timeline. It's so here we in the bottom here in this, and now we're on the red triangle BGH. Right here, I'll use my handy dandy again here. We have a clock at H that moves along the direction of this observer, which I put on a red line. The observer, there's actually three observers here. The one traveling on the red line, the one traveling on the green line, and the one traveling on the blue line. Now, let me think, why do I need three? Because, I'll tell you why I need three. If you just have one observer, then when you're looking for an invariant, so you're seeing what doesn't change when you have different observers. So we have observer B, the green guy, call it, observer, 2. Observer 2 traveling on the green line looks at these clocks. And it's the same interval. If you could blow these clocks up and read the time, it might be some fraction of a second, right? And these these observers, the blue observers, got to come look at the situation and come up with the same for that particular interval between those two clocks, which you could take a picture of their faces and get the time difference. Both of those observers, in fact, all of the observers have to agree about that interval. And so you have to be able to state that in the theory. And Einstein called it the invariant, because you can't change as you jump from one observer to the other, because it's part of reality. And everybody in physics needs to agree with aspects of reality. So now right here, this diagram is drawn to scale where c equals 1. When you draw momentum, momenta, and the angles here, the diagram basically equates on the same level, time and distance, like distance in meters. So the units then become such that the speed naturally becomes 1. It's like a nice tendency, a very strong tendency, the way, if you draw it, that it works out automatically that way. So just so you don't forget, notice here at the c equals 1, I put it over here again, c equals 1, c equals 1. I just get very tired writing c in everything. So in this case, there's already, the diagram's kind of busy. But, and let me remind you that there's two right-angled triangles, AGH, and also this HBG, and the interval is HG, and there's this clock has a value at H, and the clock has another value on the face at G, and the difference between those two is a time interval. And anyone who looks at these two clocks at these 2 points, like one clock at these 2 different time points, so it's they have to agree. So let's look at what this says. Observer 1 times, remember it's a right-angled triangle, so the diagonal squared is equal to the sum of the squares of the 2 sides, right? So what's this? Observer time squared. What's the observer time? Time 1. So that would be, I have it right in here, and it gives you the observer time 1 squared, and that's HA. So let's look at what HA. HA is the time recorded, because this is the observer, the blue observer, the observer 1. He's traveling along the blue momentum line. So, and he goes from H to A. So that's his time. So HA squared is his time squared minus AG, and it's the distance from him to the observer or the clock traveling on the red timeline. So minus AG squared is equal to, down here, the time interval HG squared. So that's going back to, I'm going to jump back up to the yellow triangle. Okay, so it's the same thing I just talked about. Very same thing. So this is the diagonal. There's the right angle. The diagonal squared minus this AG squared is going to be equal to HG squared. That's Pythagoras. It's one of the simplest principles described in physics. Okay, so this is a simple thing. Now let's go to the other chart when I'm talking about the small triangle now, because I'm referring to the green observer. Now his observer time, which is HB squared minus x1 squared minus, and that his distance is BG. See, right over here I put the little hint. It's BG squared. His x1 in green, his coordinates x2, x3. These are distance segments. Anyway, it's BG squared. Okay, and both of those guys agree on the time interval squared. Okay. So now this is actually so simple again. It's so simple that some people's minds can't process it. Okay. Now I'm very happy with that, and that's the way. This is my native language. This sort of thing, these charts. Now, enter Minkowski. Herbert Minkowski, I think it was Einstein's teacher, and later became his co-worker. And he convinced Einstein. Einstein rebelled at this first. He didn't want to substitute ICT for T. And I think CT you got to do because you don't get this nice geometry otherwise. But to put the square root of -1 in there, when you take the square of things like observer time squared, right? If it's ICT, you're going to get I squared, C squared, T squared, basically. Is that true? Yes. So the I squared makes it negative, and it kind of it changes the things around. But it gives you a beautiful invariant, a beautiful form of the invariant, which is mathematically easier to work with. And that's finally Einstein gave in, and he did it Minkowski's way. And we can do it the other way. I mean, like I said, I'm a design engineer. I design things but according to spec. And if I want to spec it a different way, I could spec anyway, anyone can do this, spec their own, and as long as it matches, you know, the physics of it, you can make the mathematics, the model, operating according to different rules, you know. It's just, does your model match the reality? So that's what the specification has to achieve. So we're going to substitute ICT for time per Minkowski. So here we have, and remember, I put C equals 1, C equals 1, C equals. So we don't have to worry about the C. Just put that's why I did it. You just put the I in there. So for all the times, you got to multiply by I. I did that, okay? And notice there's a negative sign here. Well, when you do a negative on one term, you have to do negative on the other term too, and it's and on the other side as well, and of the equation, if you negative one part. So what happens is, and you can follow through the arithmetic, but if you arbitrarily make one term negative that isn't, then the term that is negative has to go positive. It flips it. So that's what we see here. We put the I there, which is going to introduce a negative to just this term, and then this term, which was negative blah blah blah, suddenly has to be positive just to make the arithmetic work. And the same with this other thing. And then the time interval hd, that one has a negative, so you're putting a negative across both sides of the equation. Now, if you say 2 times 2 equals 4, and that's true. Now if you say negative 2 times negative 2, 2 times 2 equals, oh no, that's not happy. If you say 2 plus 2 is equal to 4, then if you say negative 2, it's funny, I'm getting stuck on the 4. We're going to have a lot more talk about the 4 here. I'm improvising right now, and I got to think about it for a second. Improvising. Yeah, if you say 2 plus 2 is equal to 4, then if you put negative signs on both of them, minus 2 minus 2 is going to be equal to minus 4, okay? So that's why we put the I on this, the time interval, hg, as well. And it all works out. And what that does, I'm sorry to put you through that, but Minkowski puts us through this. And once you just get, I would, if I was you, I would do a screen save and print this out and just look at it. And it's all so simple. It's as simple as 2 plus 2, right? It's equal to 4. And you saw me have to think about it. So it's even as so simple that it's mind-numbing. Anyway, what you get is x squared plus x1 squared plus x2 squared plus x3 squared plus x4 squared is equal to I times the time interval squared. It applies for these two observers and all observers. And Einstein called that the invariant because it applies to all observers looking at this interval, time interval. Okay, so we did that. And so x1 squared plus x2 squared plus x3 squared plus x4 squared is the invariant for special relativity. A very simple thing, and it's immensely powerful and used to produce Einstein's gravitational field equation, as we will show next. Okay, so like I said, in special relativity, the invariant, according to Minkowski's method, is x1 squared plus x2 squared plus x3 squared plus x4 squared. Very nice. You can see how mathematically it's nice and clean. And that which I just said, all the squares and is equal to x1 plus x2 plus x3 plus x4 as a row vector times x1, x2, x3, x4 as a column vector. Now here comes a rule that it actually could be changed and be described a totally different way, but I'm going to stick with the rule the same way mathematicians and physicists do. They adhere to it as if their life depended on it. So then the rule is multiply row times column and add, right? So then you multiply this row times this column and add. So you get x1, x2, you get x1 times x1 plus, which is x1 squared, plus x2 times x2, which is x2 squared, and x3, times x3 is x3 squared, and x4 times x4 is equal to x4 squared. And then you look over back here. Let me do it. It's kind of a shock because you see it right there. It works. Yahoo! Okay, we're going to do more of that. Remember that row column stuff because it's necessary to stay on that rule. Like I say stay on that rule because it's almost like driving on the what do we drive on? I have to think about everything. You're going down the road, you drive on the right hand side, I think. Anyway, if I'm wrong, it wouldn't surprise me. It's arbitrary. The energy density exerts outward pressure on space-time, and this pressure curves space-time so that we get these instead of x squared, x, and 1, 2, 3, 4, we get y squared, y2 squared, y3 squared, y4 squared. Now, these, if it's highly curved, those variables are going to be different, and the invariant would not be so retrievable, right? So we're going to compare this to the invariant for special relativity, which is x1, x2, x3, x4. And I make them red, so you got the green one and you got the red one. And I'm going to keep that, I think, throughout this presentation so you can tell when I'm talking about curved space and when I'm talking about more or less flat space, which is special relativity is flat space and general relativity is an extension to the curved space as well. So to restore the invariant x1 plus x2 squared plus x3 squared plus x4 squared from special relativity, we need to take the curves out of x1, y1 squared, y2 squared, y3 squared, y4 squared. So let's do that. So this is where it gets funny, because the model, we don't want this y, things in y's. We want an invariant. We want to get back our invariant. And then we can write the gravitational field expression, right? So what we do is we're going to do it by making the model do it. So I say here, to restore the invariant x1 squared x2 blah 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 for special relativity, we're going to now take the curves out of y1, y2, y2, 3, y4, so that we can reproduce the invariant for special relativity. So, wow, we're going to gerrymander the model to output what we desire, which is to have this invariant from special relativity, the same invariant from special relativity. It's amazing. So we start with, to get, remember row times column, take the row times the column and multiply them together and add, right? So it's y1, you get this y1 squared, y2, you know, we've been through that. So that's where we start, and what are we going to do with, okay, so what we need is we have the row times the column. And right now, if you have the row times the column, we just did that. We get y squared, y1 squared plus y2 squared plus y3 squared plus y4 squared. We don't want that. We want our special relative with x squared, you know, in red there on the top. Let me use my handy dandy. See up there? That's what we want. Well, we have this. So we're just gonna get out our sledgehammer and make the model do what we want. By the way, this is what Einstein did, which is kind of funny. So let's see what this means here. Okay, so I did that. Now go ahead. So I have question marks here. So it's like, what we start out with this row vector in y, and over here, oh, I'm going to take my handy dandy again. We got the column vector in y, and it's like this one, this thing with all the questions marks. You have to have this one here that I'm showing with the question marks, the one over towards the right. That one, that one times the column vector has to be able to produce a column vector in x. Okay. And this one over here, and I'll tell you why it has to. And this one here, y and y, times this one with all the question marks, and it's on the left-hand side. Those two multiplied together have to produce a row vector in x. Because, here's why. Because a row vector in x times a column vector in x will give us the x squared 1 plus x squared 2 plus x squared 3 plus x squared 4. That's the invariant that we seek. Okay, we want to extricate that same invariant that we found in special relativity, and we're going to make the model do it because it's our model. And that's Einstein did it too because it was his model. Okay, so let's do that now. To iron the wrinkles out of space-time, we need to solve the following. And I have a nice little picture of, you know, this is what we're doing. We're ironing the wrinkles out of our model, okay? So let's break the two problems into, and focus on one at a time, okay? So we're going to focus on the problem on the left here. y1 plus y2 plus y3 plus y4 times question mark is equal to x1 plus x2 plus x3 plus x4. We want to get that row vector in x. Can you imagine? Oh, wait till you find how they hide this. Because they don't want to let people know that they took out a sledgehammer, they arbitrarily, you know, smashed the model and flattened it all out like ironing a shirt. So, anyway. So, and then also, once we've solved that one, we're going to solve on the problem on the right, which is right here. You can see it. But I want to focus on this one first. So let's see what we got next. All right. Oh, I solved the one solving the column vector first. Okay, let's solve this one first. Okay. So Now, I actually came up with this myself because and see, it's a simple. It looks horrible, but when you know what you want, it's actually pretty easy. So just watch how this works. If you take this particular row, right, and you multiply it by this column, and which is in y's, right? But notice on the top is delta d. It's a different. I don't want to use the words, but if you're like math and all that, it's a differential. But it just means the rate of change of x1 with y1. Okay, the rate of change of x1 with the change in y1, and then the rate of change in x1 with the rate of change of y2, and the rate of change of x1 with y3, and plus the rate of change of x1 with respect to the change in y4. Remember, y4 and all these things are curved, and they're changing as you go up and down them, and it's changing x1. They're linked, okay? But it's all about x1. So when you take, for example, you do row times column. Here's the column is right here. Column is the one in green here. Okay. So it's in y. It's the curved part, and you take the row here is this whole thing. So you get d, the rate of change of x1 with the change in y1 times y1. Now y1 is some infinitesimal. You know, Einstein does a lot of leaving out of things and implicit. And so I'm doing one thing here. When I say y1, I'm sick of writing a little triangle and saying it's a delta y1. It's a small y1. But that's implied, okay? So what you have, you multiply this term times the first term here times y1. Remember, it's multiply and add. So you get dx1 by dy1, right? Or the rate of change of x1 with the change in y1, and you multiply it with the change in y1. Well, of course, you get the change in x1 due to y1, right? Okay. So you get, and then but it goes it's row times column, so you multiply the whole row times the whole column, and you get all the little bits of changes. The change in, you know, for the example, the next one, because you multiply the row times the column and you add them, and that goes into x1. Okay, all of them are x1s, not x2s, not x3s, not x4s. So when you do that, you get a little bit from y1, and you get a little bit from x2, a little bit of x1 from x2, you get a little bit of x1, delta x1 from y3, a little bit from y4. And when you add them all together, you get x1, right? You get x1. So you've converted y1 into x1. Wow! You made the model do it. It's so great. So then you can look at y2, same thing. You do row times column, right? And so it's the change in x2 now, not x1. x2 with the change in y1. And the next term is the change in x2 with the change in y2, right? And then the change in x2 with y3, change in x2 again. It's all x2. It's not x1 now. It's not x3. It's not x4. It's all x2. So you multiply this row times this column, and you add, and you get x2. Wow! You've just converted y2 into x2. It's amazing. So, and then you do it for y3, and all the changes with the, you know, x1, y1, y2, y3, y4, the changes, you know, and you get y3, x3 rather, from y3, you get x3. And the same with x4 here. You take this row, the bottom row, multiply it by this column, and it creates the new value for x4. So you've created the column vector in x, which is what we wanted. Okay, so that produces the column vector that we're looking for. Remember, what we want is the invariant from special relativity. And to get that, you need the row vector in x times the column vector in x. We got the column vector in x, so we know that this piece has a role to play. Now let's go to the next one. All right, now let's solve the second expression, which in this case is the one on the left, okay? So we do the same thing, except now we multiply y1 plus y2 plus y4 row, which is this one row, times column. So there's going to be 4 terms. You take this one y1, y2, y3 plus y4, and you multiply it by the first column, and you get the first term. It's all in x1, okay? There it is, x1. Then you take this same, I gotta use my handy dandy, take this same row here and multiply by this second column, and we get x2. It's all the little bits of contributions, which when you add them all up, you get x2. And then you take y3, well, this whole thing, and we multiply by column 3, and which has every one of the changes on the numerator is x3. So you get all the contributions which lead to the total x3. And then you take the same row here and you multiply by the fourth column and add, multiply and add, and you get all the contributions for x4. We get x4. So now we've produced the the desired row vector in x. Remember, we wanted to get the invariant from special relativity out of this situation in curved land, though in y. We wanted to get we need to have the row vector in x multiplied by a column vector in x. We got the column vector, we got the row vector in x right here. Whoops. What am I doing here? Right here. And previously, I'm going to go back a chart, we produced the column vector in x. So we have the components now, we just have to put them together. So let's do that. Okay. So here what we have, I've put the left-hand solution, I put the right-hand solution, multiplied them together. We know that produces yeah, I even say here this portion of it, these first two components here on the left produce the row vector, and the second two components on the right produce the column vector. And when you multiply those together, you get the invariant that we're seeking. But we got it when working on y. It's amazing, okay? So we get x1 squared, x2 squared, x3 squared, plus x4 squared, which is the invariant that we were seeking, okay? So we are very close, guys. Very close to finishing this up. Now, okay, now, here's the part that I find so hilarious. We basically beat up the model and made it do what we wanted, right? And I kind of find that funny. I guess that's a lot of physics. You know what you want, you make the model do it. Because really, physics, from a modeling point of view, the model is not the reality. But you want the model to output some attributes, some relationships that match what you find in reality. And you don't really care too much about how you're doing it, as long as it friggin' outputs the results that match reality. Then you're happy. Of course you don't, outputs the results that match reality and don't match anything that is not in reality, right? That is definitely not in reality. Like, you don't want to violate what is already known, right? So that's what we're trying to do. And now, here's the funny part. They take these two, kind of like I'm going to say it, it's not really, but it's like a fudge factor. Because you strong arm the model to produce the output you want, which is acceptable. But here's what, and it makes total sense. Now, if you were to take these two tensors and you multiply them and you just name them G subscript UV and call them the metric tensor, right? G subscript UV, and not relate it back to this at all, right? A metric tensor. It doesn't tell you anything. It's like so mean. It's like you sweep the path that you've gone down after you get there. It's like you climb up the building and you using a ladder, and then you take the ladder up and burn it, right? And then say, hey, everybody, come on up. I went up there. It's beautiful up here. Come on up here. You know, it's kind of like that. Well, anyway, I find that really kind of funny. Here it is, though. GUV is this. So now you know what GUV is. It's right there. No big deal. And we know these are the components of Y, and we know they're bent. And here are the components of X. We know they're not bent. So this is what we're looking for. Now there's something. The form here is still not what mathematically minded people would like to have, and I think I'm going to put a space in. Geez. I guess can I do that? Let's try it. Yeah. Okay. So I wanted an extra space, save it. So the mathematically minded, I did a little bit of that myself. I wanted the space here. You see here, if you put GUV in front of which I did here. Let me see. I'll show you. GUV here. Move it from that position to this position. In front. Now you have y1 times y2 plus y2, y1 plus y2 plus y3 plus y4 as a row vector times y1, y2, y3, y4 as a column vector, and that we know it produces the desired result. But you know, I think I should color this green. Let me do that to keep it consistent because it's in Y. Green. What is that green? Is this green? Yeah. Right. Okay, good. Let me save that. Now, then we get this down here, and this is the sort of thing that mathematicians really like, because it's GUV is this special thing for general relativity times the measurement intervals, small distance increments in the different directions, squared. That becomes the invariant for general relativity. Now, general relativity has to explain special relativity as well. It's generalized. It's not narrow in any way. So this becomes the new invariant right here. It's beautiful from a mathematical point of view, and I think it has a lot to do with why Minkowski, insisted that they go down this way. So there we have it. So let's see what's next. Okay, so I repeat this entity here. By the way, these things, after I discovered this myself actually, and I didn't know what it was called, and but I went looking to see if I could find it somewhere, and I finally found it, and it turned out it was called the Jacobian. It was from a mathematician, I think it was 18 and something or other. Son of a banker, came up with it, not for this reason, but and so that's this thing. Let me use my handy dandy again. This portion here is a Jacobian. Notice it's x1, x1, x1 on the row, x2, x2, x2 on the row. So the numerator is the row counters, and like row 1, row 2, row 3, row 4. And notice the denominator have column counters. Column 1, column 2, column 3, column 4. So it's a very simple structure, of which I see this one here. Simple, but you got to put it in there. Somehow I lost it. Put it in there too. The little delta. Yeah. Good. So there we have it. That's the Jacobian. Now, what this here, because mathematicians want to keep the row column thing, and without changing it. It's like driving on the right-hand side of the road in North America. You don't want to change it. Things can really screw up. So what they did here to make it work is they took this one in the Jacobian. They took they had to take, and I actually had to take it too when I did it, to match my specifications. I had to do this as well. Take the first column here and put it in the row. See, x1, x2, x3, x4. See, so you swap rows and columns. And the next column here, that would go in the next. The next row here goes in the next column, right? x1, x2, x3, x4. And the next row goes in the next column. So you swap rows and columns, x4, see? And the last row goes in the last column, right? Starts out x1, and then it's all y, the row here, y, dy4, dy4. Yeah, it's all dy4 too. So that's what it is. This is, they call that the transpose. And it's what's needed, so that's what we have. So it's a transpose of the Jacobian here. And these are just names. I'm not that interested in names. This is the Jacobian, and this one is the transpose of the Jacobian. You multiply them together, you get G of E. And you get G subscript UV times the components in Y squared is the invariant for both special relativity and general relativity. So it's a generalization of successful generalization of the whole concept of invariance, extending it from just sort of flat spaces and to include also curved spaces. So now let's look at this. It turns out that G superscript UV compared to G subscript UV, it flips the derivatives. So, and the result of that is that G superscript UV undoes what G subscript UV does. Now, it's like, let's say you multiply something by G superscript UV, and then you multiply that by G subscript UV. Well, G superscript UV does something to the entity, and G subscript UV undoes it. So it leaves whatever you're multiplying the same. It leaves it the same. Now, if you multiply by 0, it doesn't leave it the same. It gets rid of it. If you multiply by 1, it leaves it the same. And these are 4 by 4 tensors, right? So you need it to leave it the same. You have to multiply by a matrix with 1s down the diagonal, right? 1s down the diagonal. That's 1 in 4 by 4 tensor land. 1 in 4 by 4 tensor, and you have to have it 1 because it's not changing it, right? And so that means that G subscript UV times G superscript UV is equal to what they call the identity matrix, right? And we're talking physics here. So when you have these things laid out like this, they all add because they're all part of nature. So if you want to know what the total is, you add them. And that is 1 plus 1 plus 1 plus 1 is equal to 4. So this, we kind of just looked at it, and we derive what that G subscript UV times G superscript UV has to be equal to 4. And that turns out to be so critical. You know, we're almost at the end. We're almost derived Einstein's gravitational field expression. not quite. So here we go. Boom. So over here we have on the top, I'm going to get my handy dandy, G subscript UV times G superscript UV is equal to 4. We established that. Now remember way back we started with the first tentative statement that curvature is equal to K times mass density. In other words, the curvature is proportional to the mass density, and the K is the constant of proportionality. Now in my series, General Relativity 1 through 6, I actually derive K. So if you want to see that, you can go look there. So we write that down, K times mass density. Okay, so RUV is a curvature tensor. It is equal to K times the tensor for mass density or energy density. They're the same, you know. Especially if C is equal to 1, they are the same. So that we have that. Now, let's start with this. We start with this. Now, this is then we accept as being a true start, okay? Now, I'm going to say something so simple. If you have R subscript UV is equal to K times T subscript UV, now that means that if you have R subscript UV minus 1/2 times 4, which means minus 2, think about it. What's 1/2 times 4 is equal to 2? Okay, great. Now what's minus 1/2 times 4? It's equal to minus 2, okay? So, any doubts about that? I mean, simple things like that can really buzz your mind. So minus 1/2 times 4 is minus 2 R subscript UV. So if you have R subscript UV, and that's equal to K times T UV, if you subtract 2 of those, then the first time you subtract K times T subscript UV, you get 0. And then you subtract it again, you get negative K times T subscript UV. So we're on to this step now. That's what we have here. Now, notice we have 4 right there in this expression, 4. And we know that 4 is equal to G subscript UV times G superscript UV. So we put this in for 4 here, and we get this. Okay, we just put it in. And that's the same thing over on the other side, minus K times T subscript UV. Okay, great. Now, what's very, very interesting is when you multiply, it turns out that when you multiply a tensor like R subscript UV by G with a superscript UV, it basically cancels out the derivatives cancel out between G and R, and you just get R as a scalar version of R, okay? So that what you end up with then after that is R subscript UV times the minus R subscript UV minus 1/2 times GUV times R is equal to minus K times T subscript UV. That's what you get. And guess what? That's Einstein's gravitational field expression in full. Well, he added things later on, cosmic coefficients and things like that, but I don't want to go in there. I want to deal with the basic gravitational field theory. And here it is. So, let's put some names to it. Now, I don't like names very much because they don't mean anything. They're just nominal. But it does mean a little bit in the sense that a lot of these things also have been worked out by Riemann. And this turns out to be, this R subscript UV, they call it the covariant Ricci, I call it the covariant because it's got UV on the bottom. Covariant Ricci tensor, okay? And then this G subscript UV is the covariant metric tensor, okay? And R remember, it takes the directionality out of it so it becomes a scalar. They call that the Ricci scalar. And minus a half, it was necessary for the reasons we just went through. And over here we have this K is, I think it's called Einstein's constant because he worked it out. And I also derived it, and I think it was General Relativity 5 and 6, my videos there. And the T subscript UV is the covariant stress energy tensor. It's covariant because this UV is on the bottom, and it relates to the derivatives. I don't want to go into all the math because the point is to explain it in a way that is understandable by a young person, and it's not to explain all the details. That's not what we're doing here. And general relativity is, first of all, it's a macroscopic theory, and it doesn't have yet. In the current form, which I'm trying to maintain felicity with Einstein's original thinking on this. After this one, I'm going to deviate and start doing some necessary, which I'll explain in another presentation, changes. And yeah, I can't talk about that right now because we're still trying to explain Einstein's gravitational theory as what formulated by him. So let's have a review now. What did we do here? First, the idea was to explain general relativity to a young person, and not all the details, but have them understand the basics and why it should be this way. And I hope I've achieved that. Let's go through. We were going to look at the relationship between mass and energy by inspection. We did that. It's E equals mc squared. Why mass curves space-time in the beginning of the formulation of model of general relativity? Yes, we show that if you take momentums like such as arising from the energy emitted from a Hiroshima bomb, and you run it backwards by attacking it with changes of momentum coming in from an external and compressing, put it back the way it was and when it was plutonium, or I think it was uranium at the time. You compress it back in there, the pressures are enormous. Well, that's the situation within matter. So that pressure finds its way out into pushing on the vacuum itself and curving space-time. And that's why we expect curvature. It's why Einstein expected curvature, and we have curvature. The next one was why mass curves space in the beginning of the formulation of the model. The beginning of the formulation of the model is that the energy density or the mass density should be proportional to the curvature. And that's the initial expression that we started to work on. Yeah, I should comment here, in General Relativity number 6, I went through and showed that for it to be a physical theory, you need to have the structure of the gravitational field equation. When you take the derivative of it, the derivative of the stress energy tensor, because it's a mass density, and like for the Earth, for example, that should not change. So the derivative is equal to 0. You have to make sure that the other side, the curvature side, also behaves itself and has a derivative equal to 0. I'd go through that and prove it. We're not going to do that here for obvious reasons. We're explaining it to a young person. But it's in General Relativity number 6 if you want to see it. Okay, so let's look here. A quick review of special relativity enough to derive the invariant. We did that. It's, all the red, x1, x2, x3, and the squared each term. And we also showed how important it was for deriving Einstein's gravitational field expressions. And you had to do it according to Minkowski, the way that Einstein formulated it. Constructing a procedure designed specifically to extract the invariant from special relativity, starting with the measurements from curved spacetime. We showed how to do that. And then the really interesting way that they expressed it at the end. And then making the procedure sound respectable by calling the major portion of it the metric tensor, which I find kind of funny because they just call it G and they expect you to somehow magically see what all that is doing. Or actually, I don't think they do expect you to see it. And I don't know why they have done that so often, but they did. They did. So the metric tensor multiplied by its inverse equal to 4, we did that. Deriving Einstein's gravitational field expression from the initial model plus the metric tensor and its inverse. We did that. So we achieved all our objectives, and hopefully you understand how you can explain general relativity to some young person, and maybe you can try that. I find it's very easy to hold in my mind, and recently I actually tried. I don't have to look up any of these things, even if years go by. And I tried to explain it to somebody after purposefully having a couple of beers to see. A beer is a disaster for my mind, like it was for Richard Feynman. The reason why I did not drink. Anyway, I could even explain it when I had a couple of beers, which I rarely do. Which I think shows that it's really not that complicated. And I hope you enjoyed that. I really enjoyed presenting it. And with this, I think I will say have a good day and thank you very much.